Hello everybody. So in this part of my talk I want to go a step further concerning scenarios. I want to explain simulations which we have done with more complex tasks, and thus I would like to introduce more complex model scenarios. So far we investigated or we simulated a simple production task, this picture naming task, the comprehension task, and the simple repetition task. And we investigated how the performance of these tasks change in the case of introducing specific neural dysfunctions as they occur in different types of aphasia. So now I would like to focus on still more complex tasks. Yes, why? In order to demonstrate the realism of the model, I will give more information concerning this on the next slide. So the first more complex task I would like to introduce is serial recall. Then again, two cases of picture naming, but in this case with the introduction of distractor words or doing picture naming in the case of problems with lexical retrieval and and with introducing or including cues in order to get a better performance for the picture naming. So why more simulations? I already gave the answer. In order to demonstrate the realism of neural models, what we already demonstrated is that this neural model works in the case of normal behavior as it was shown for naming, picture naming tasks, simple comprehension and simple repetition tasks. But that perhaps can be modeled with a non-spiking, a simpler neural model. Cases for which the spiking neural model and the statistic behavior of neural signals is important is for the simulation of rare cases. I already introduced that as well. That means we can have a fail in naming. No naming is done, or no correct picture naming is done in less than 1% of all simulations for normal speakers. And we have already discussed that may be due to some statistic processes which may occur in neural signals, because these neural signals are at least statistically varying signals, noisy signals, at least signals based on the spiking behavior of neurons. And we introduced the neural dysfunctions. We simulated symptoms in the case of different speech disorders. In the case of this more complex simulations I would like to introduce now, we want to simulate overburdening that may happen in the case of a serial recall of many words. We can't give the correct 15 words back in a serial recall task, so it is an overburdening situation for the model, for the person who's speaking, who's doing this task. And yes, which is more or less the same. So we try to simulate difficult tasks in order to generate more faults or more mistakes. So that is done in cases in which we try to simulate speech errors, as we will do by introducing distractor words in the case of normal naming, picture naming tasks, or we will try to generate more mistakes by using tip of the tongue situations. That means in the case of lexical access problems, we may generate wrong words in a picture naming task. So, first of all, I would like to concentrate in this part of the talk on the serial recall task. I have not done this simulation by myself. I refer to the work done by Xu in 2010, and he used the NENGO simulation model, and the input were 10 or 15 words, and it was the task of the model to repeat these words in the correct ordering, which is called a serial recall task. And the result which we find if we do this experiment naturally or in simulation is that we get lowest repetitions rate for words which are in the middle of this word list of 10 or 15 words. So the result graph becomes concave. I will show that in the next slide, or in the next slide. In the next slide, I will just focus on the fact that this serial recall task mainly concentrates on the cognitive component of the model, and it introduces short-term memories and binding processes concerning the positions and the words themselves. So this is not introduced here in our architecture. Oh, I'm sorry. So in our architecture, we have to introduce here more buffers for first of all, buffers for realizing short-term memories and buffers for realizing binding. So the results which we get are given here from the work of Xu for natural data, for the serial recall of 10 items, I'm sorry. So here are the serial recall data for 15 items, here for 10 items. And here we have the model data, here for 10 items and here for 15 items. That is given wrongly here. And what we see here is a probability for the successful recall. And the recall is done directly here after no delay and with a delay of 3 seconds, 9 seconds or 18 seconds. And what we see is already this concave structure. That means the words in the middle have the lowest probability for successful recall, but while the first and the last words have a higher probability. And what we see in the simulation, in the model data, here for the 10 items, here for the 15 items, is that this concave behavior can be reproduced slightly. So qualitatively, the data can be reproduced, but what we see is a quantitative difference. At least the model is too good. So maybe the short-term memory works too good, so we get too high recognition rates, especially at the beginning. That means for the first words in the word list, which is used for the serial recall. So that's typical result for neural simulation models. We are already capable of modeling quantitative effects, but sometimes it is difficult to get the quantity of the modeled data already totally correct. So there may be some discrepancies in quantity, but mainly not in the quality of the results. So the next talk is the next scenario, the next simulation task is a picture naming task, but now we introduce phonological and semantic distractor words, which are acoustically introduced directly after we instruct the model to produce, to utter the word. For this case, we use a specific word list including phonological and semantic, similar and dissimilar words, because from natural data we know that distractor words seem to have a different effect whether these words are similar or dissimilar on the phonological or semantic level with the target word, with the word which has to be produced during the picture naming task. So first of all, here is this word list. So we are doing we're doing simulations with 18 target words. These are introduced visually, and the acoustic distractor words can be semantically similar, phonologically and semantically similar, or dissimilar. For each word and each distractor word, we are doing three simulation tasks. What we will see if we look in the activation of the model buffers during this simulation, that we are able to generate halts or no or late halts in different cases. That means in different cases of distractor words. And we can get this by including an evaluation of the similarity of the items. That means of the target word and the distractor word. Yes, by evaluating this similarity at the phonological and at the semantic level. Why can we do this evaluation of the similarity of these items at this level? Because we have the internal feedback loops. Perhaps if you remember the earlier parts of my talk, we have three feedback loops at least included in the model. The first is the main feedback loop, the external feedback loop, which uses the auditory or the acoustic output, which is processed by the auditory system again. But we as well have internal feedback loops. The first is a semantic loop, the second is the phonological loop. Here, it means this at this level. And yes, at these levels in the production pathway of a word, we have these feedback loops in order to see that here we try to produce the correct word, which we have in mind for the production. So we can compare the similarity of both activations. And we can do that at the phonological level as well. Here we can see, or here we can try to check whether this phonological realization is correct in the case that we perhaps can remember the phonological realization we want to produce. And that is on the perception side. So, and if we now introduce distractor words from the acoustic level, we may get here discrepancies because we have here a different distractor word. We can get discrepancies here concerning the phonological similarity, and we can get discrepancies here on the concept level concerning the semantic similarity. And we try to evaluate that, and if there is a low degree of similarity on the semantic or on the phonological level, we give a we evaluate that and introduce that to our control component, to the control process, and introduce here a new control action which allows the model to stop the production here. The production starts here at the motor level and goes here to the speech organs to stop this production if the similarity here between the perception and the production side is not strong enough, so that we have the impression we are producing a wrong word here. So that can be done by the distractor words. So the distractor words are given acoustically. The target word which should be produced is it is a picture naming task, so this is simply the target word is given as a visual input. Okay, so we have 18 items, 3 runs for each item. That means 54 simulations per item for each case, for the case of similar and dissimilar destructor words on phonological and semantic level. Yeah, and we see the result for the model version, including the evaluation of the semantic and phonological level here. So first of all, I have to say, so we can generate HALT events, and this occur in the case of dissimilar destructor words mainly. We see that here in the case of dissimilar destructor words, we have a lot of HALTs during our 3 runs, because the whole number of simulations, the full number is 54, and we get here already 50 halts in this case of this model. In this, yes, and we get what we will see during the simulations. We suppress the halt signal. At least we cannot suppress it totally, but we can suppress it from early points in time. So we can delay the halt signal in the case of similar destructor words. And this occurs really in most cases. Only in 2 cases we have a strong halt signal, and in all other cases we have non-strong or suppressed early halt signals. Okay, that is more or less in accordance with natural data, but what we directly saw, if we use this version of the model, including the semantic and the phonological level evaluation, that we get is not a strong suppression of the halts in the case of phonological similar words. So we introduced a second version of the model in which we evaluated just the phonological level. And then, yes, then we got at least too many stops in the case of the semantic similar words, but we get a better fit of natural data for the phonological level. But I will come to this later on. So, first, the case phonological and semantic dissimilar words. I will show now a simulation for a target word, and the destructor word is phonological and semantic dissimilar, and we will see that will generate a strong halt signal directly, and the word will be not produced. So how is this realized in this task? First, let's go to the input. We see the auditory input of the destructor word is fox. It's coming here. We have already earlier given the visual stimulus, the visual input. The word is train. So both words, target word and destructor word, are semantically and phonologically dissimilar. And yeah, at least the priming process is the same as in the normal picture naming task, which we discussed already in earlier task. But now, in the control component, it is possible, if we have here this dissimilarity between these target and destructor words, that in that case we are able to generate a strong halt signal, which occurs here. Here are the utility values. So first of all, at the cognitive input level, we get the realization of the visual input. Sorry. And we will see at least this word is really generated as well at the cognitive output level. And we see through the production pathways at the concept and lemma and phonological level, the target word train is produced as well. At the phonological level, we see that we have a disturbance by the destructor word, which is occurring here at this point in time as perceptual input. On the phonological level, he is going up to the lemma level, here to the perception level, to the concept level. Yeah, and here we see the interaction of both words. This is evaluated in the loops as I told earlier. And what we see is that, I go back to the upper part of this figure, that we generate a strong HALT signal in the control component of the model, which produces a strong stop signal or a strong nil signal in order to interrupt the production of the target word at the motor level. So we get a stop here at the motor level. So we will have now a look in the in the other case, phonological and semantic similar words that should not produce a strong HALT signal, but in the version of this model, we could better say it suppresses an early HALT signal. Yes, and that's directly what we see here. So the acoustic input is Charlie, the perceptual, the visual input is train, so that is similar on the phonological as well as on the semantic level. And we see that in the result we get a HALT signal which is delayed in comparison to that what we saw with the other distractor word in the earlier simulation. And what we get is more or less here the same things. We can go through all these buffers and we see that the HALT signal, which is delayed, leads to a stop of the activation of the motor level later on. So at least here in this case, we have 400 milliseconds already an activation of the motor plan level of our model, which may be enough time for activating the whole articulation process for the word train. So last but not least, I would like to discuss the case that we use two different models. At least I introduced that in an earlier slide. The reason is that in the case of evaluating the semantic and the phonological level together, we get two weak suppressions in the case of semantic similar and phonological, two weak suppressions in the case of the phonological similar words, but two strong suppressions in the case of semantic words. If we take the second version of the model, in which we do not evaluate the semantic level, we get two strong suppression of the phonological similar, in case of the phonological similar words. So at least these results, these quantitative results, give us the idea that we perhaps could change the model, because both types of models do not give the quantity realistically, the quantity which we get from natural data. So we could adjust a parameter which introduces an evaluation of semantic and phonological level, but the semantic level not as strong as the phonological level. But we are not doing this here, because one of the basic laws in modeling is do not adapt model parameters due to experimental results. I would like to go to this point a little bit in more detail in the next slide. So, a basic law of modeling is that modeling needs to be straightforward. That means we have to define the model qualitatively and quantitatively on the basis of rules which are just coming from the neural functioning level, from the neural level. They are coming from the bottom. And then we use the model developed on this in order to generate simulation results. These simulation results are qualitative and quantitative, and I told, or I discussed earlier, that the qualitative results are always good in case of our modeling, but quantitative results are sometimes a little bit unexact. They are not, maybe a little bit too high or a little bit too low, which would give us the chance to adjust the model, but that should not be done. That means we should never change or adjust the model on the basis of the quantitative results we generated. So, what we did in the case of this study, for the model we used here, is that in all cases, for the neurons and the neural connections, we use the default parameterizations given by the NENGO framework, and we suggest a post-adaptation of the model only in one case, which is indicated here by the black arrow, so that we take the calculation, the similarity results here from the semantic level and from the phonological level, and adjust this in order to produce here by the control component as a HALT signal, which affects the production on that level, as we saw by the simulations discussed earlier. So at least we can adjust here a parameter which influences the strength of the generated HALT activity here. Yeah, but at least we should not do it. At least it is the best here mainly to evaluate the phonological forms. But at least we have a new information that maybe the phonological form evaluation, the evaluation of the phonological similarity between production and perception level seems to be more relevant and more important than the evaluation at the semantic level, in order to generate a correct behavior for this picture naming task with distractors. So we will come to a picture naming task in the case of lexical access problems in the next part of the talk. Thank you so far.